So where do we get started now? Well, we can get started at the very beginning. What is organic chemistry? And now, we define organic chemistry as very broadly as the study of carbon-based compounds. So of this entire periodic table that you learned about in general chemistry, here in organic chemistry, we're going to focus on one element, and that's carbon. Now, organic chemistry wasn't always defined this way. Originally, and we've got to go back 200 years now, but originally organic chemistry was defined as the study of what we call living compounds. And that's not really a definition we use anymore, or a phrase we use anymore, but really it referred to compounds that came from biological or living sources. Now, where did this change happen? Why do we go from living compounds to carbon-based compounds? Well, in 1828, there was a very famous experiment done. And this experiment is credited to Wohler. And what did he do? Well, he took a compound that was known even back in 1828, NH4NCO, ammonium cyanate. And what he did, now almost 200 years later, might not seem that significant or important. But for the field of organic chemistry, it completely changed the way we think of the field. So what he did, he heated it. So this is a symbol you may or may not have seen before, but anytime we put this uppercase delta like this over an arrow, it means that we've heated the reaction. Now, what happened to ammonium cyanate when he heated it? The result was it formed urea. And even back in 1828, urea was regarded as a living compound. Why? Well, it was known that urea was one of the components that was found in urine. And so this was a compound that came from a biological source. But what made this experiment significant is that the starting material, the ammonium cyanate, was what we would now call an inorganic compound, but back in those days we would have referred to as a non-living compound. And so this was the first ever example where a so-called living compound had been made from a non-living compound. And that eventually led to this revision in what our definition of organic chemistry is, as now we define organic chemistry as the study of carbon-based compounds. All right, so why do we study organic chemistry? And today, for many of you, the answer may be because you have to. But over the next 30 weeks, as we take Organic 1 and 2, we're going to see that there's hopefully a lot more to organic chemistry than that. So maybe the most interesting reason to many of you is biological, or biochemistry. And that's because organic compounds are central to literally everything in biology. You know, pretty much every biological molecule you can think of is an organic molecule. And so the reactions that take place within our bodies or within any organism are all organic reactions. And so we need to understand organic chemistry to understand what's going on biologically. Now, for many of us, for people like me, what interested me in organic chemistry is the idea of organic synthesis. So what is organic synthesis? So organic synthesis is how we make molecules. There are many molecules that are very interesting to us or very important to us that maybe nature provides us in very small quantities or maybe not at all. And so in order to be able to use some of these very useful compounds, we need to figure out how to make them. So let's look at an example here. So the following molecule, and you can see we actually have two structures here, but right now I want to focus on the molecule on the left, Taxol. So what is Taxol? Well, Taxol is an anti-cancer drug. Very potent anti-cancer drug. At its peak in 2001, its sales were $1.6 billion. So a very, very useful compound, and clearly a compound that people needed a lot of. The problem is where we find Taxol. So Taxol is found in the bark of the Pacific yew tree. And so it turns out if you take a 100-year-old Pacific yew tree and you strip off all the bark and you pull the Taxol out of that, you get 1 gram of Taxol. And that obviously creates two main problems. First of all, once you strip the bark off the tree, you're going to kill the tree. And second, and related to that, how many 100-year-old trees can you do that to before we start to run out? So given that they had found that this molecule had this terrific biological activity, they said, all right, we have to figure out how to make it. And so a number of chemists, in their labs with their research groups, decided they were going to try and make Taxol. And there was actually a race by a couple of different research groups to finish it. And the first group to finish it was a group run by Holton at Florida State. And while their synthesis was very nice and it worked, their synthesis was 46 steps. And the overall yield, if you recall calculating percent yields in Gen Chem, was just 2.1%. Now this seems really, really low. But in fact, it turns out this is really good for a synthesis this long. Why do I say that? Well, let's say that you manage to get 90% yield for 46 steps in a row. And I can tell you from having done synthesis for enough years that it's pretty rare to get a synthesis that works that well. Well, it turns out if you got 90% yield for 46 steps in a row, your overall yield would be 0.8%. So in other words, you've got to get better than 90% yield on every step for 46 steps to get this good of a yield. But even such, let's put this in perspective. 46 steps to 2.1% yield means that if you had 1 kilogram of your original starting material, you could make 81 grams of Taxol. So better than the yew tree, but still a very inefficient process. So what was the next step, the next idea? Well, the next idea was to look at a way to combine what nature gives us and combine that with what chemists can do in a lab. And so they found this compound 10-diacetyl-baccatin-3. Now, this comes not from the bark, but from the needles of the European yew tree. And this has two things going for it. First of all, this tree is actually a little bit more common, but more importantly, the needles are a renewable source. When you collect the needles from the tree, you don't kill off the tree. Now, while this compound isn't Taxol, what you can see is this entire ring system here is already put together. In fact, much of what I'm highlighting in yellow is already put together. And so if you could then make the piece on the left, it turns out that making this kind of bond right here is pretty straightforward. And so if you could make the piece on the left, you could combine it with the 10-diacetyl-baccatin-3 that you isolate from the needles of the tree, put those two pieces together, and it ended up allowing for synthesis of this molecule in large enough quantities that it could be used. So we talk about synthesis here because synthesis is, for most organic chemists, sort of why we do this, what excites us about organic chemistry. And while obviously in a course like this, we're never going to be looking at syntheses this complicated, ultimately that's where synthesis takes us. So where do we find organic compounds? So take a minute and think about what are some places where you might find organic molecules. So we just described one of the most common categories, and that's, pharmaceutical drug type compounds. So can you name a drug that's commonly taken that's an organic molecule? Well, that's an easy question. If you just start naming compounds like that, ibuprofen, acetaminophen, we just saw Taxol. You just keep going. Aspirin. Any common drug that you can think of, it's probably an organic molecule. The harder question would be, are there any drugs that are not, any common drugs that are not organic molecules? And there's really only one. So what's the example of a common drug that's not an organic molecule? Is lithium carbonate, which is used to treat bipolar disorder. That's just a lithium salt with a carbonate anion. So all of our pharmaceuticals, with just a few small exceptions, are organic molecules. Any plastics that you use are organic. All of our fuels, many of our dyes are organic molecules. We see many fragrances that are organic molecules. And then most biological compounds. Amino acids, proteins, DNA, lipids, and carbohydrates. All of these are carbon-based molecules. So no matter what we do, especially when it comes to biology, everything is based around organic chemistry. And so while you remember the periodic table that you studied so much in Gen Chem last year, well, sometimes those of us that are organic chemists like a slightly different version. So are we saying here that carbon is more important than other elements? I think that's exactly what we're saying. And so you'll see here, these are the elements that are most important in organic chemistry. Hydrogen, nitrogen, oxygen, chlorine, and bromine. We could make a case for adding phosphorus, sulfur, and iodine to this table as well. But regardless of that, our point here is that the overwhelming majority of what we're going to study over the next year involves about 10 elements, and in many cases, many less than that. So the remainder of Chapter 1, which will be divided up into a number of different videos, is going to be reviewing some of the important concepts from general chemistry. And that's exactly where we'll pick up in our next video, is by getting back into looking at reviewing some atomic structure as well as bonds.